Dear children, welcome to the next session on real numbers. In this, we discuss the section 1.3 of the chapter 1, the fundamental theorem of arithmetic. Before learning the statement of fundamental theorem of arithmetic, let's recollect few basic terminologies. A prime number. We all know a prime number. So one, could you recollect? A number n greater than 1, any positive integer greater than 1 is a prime number if its only divisors are 1 and the number itself. Only divisors are 1 and the number itself, that is n. So, a number that are not prime are called composite numbers. So, any integer n greater than 1 which is not prime are called composite numbers. Can you count the number of primes? It is highly impossible because there are infinite number of primes. Now we can have a small activity through which we can find out all the prime numbers from 1 to 50. Just write down the numbers 1 to 50. All the integers from 1 to 50. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49 and 50. The simple technique is to cancel the multiples of the integers 1, 2, 3, 4, 5, etc. one by one. As a first task, let's cancel out all the multiples of 2. That is all the even numbers. Let's strike off all the even numbers that lie between 1 and 50. It's a bit easy job because every alternate number is going to be an even integer. Now, of the next available integer that is not striked off, circle it, and cancel out all the multiples of that integer. Now 3 is the next immediate integer that is not striked off. So circle 3 and cancel all the multiples of 3. So it's 9, 15, 21, 27, 33, 39, 45. That's it. Now look for the next number that is not striked off. It is 5, and cancel out all the multiples of 5. Just 25 and 35. All other multiples of 5 were cancelled. And the next integer that is not striked off is 7. And cancel all the multiples of 7. So only 49 is the only multiple of 7 that is left out. Now encircle the next integer that is not striked off, 11, and all the multiples of 11 were already cancelled. So next the integer that is not cancelled off is 13, and the multiples of 13 or 26 it's already cancelled, 39 is also cancelled. Within 50 these are the only two multiples. So the next integer that remain uncancelled is 17, and multiples of 17 are 34, and then within 50 only number is 34, that's already striked off. The next integer that remains uncancelled is 19. Then the multiples of 19 is 38, and then 23. Multiple of 23 less than 50 is 46, which is cancelled. Then 29. Then we have 31. Then 37. Then 41. So the prime numbers 41 and then 47. So the prime numbers between 1 and 50 are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 47. Likewise, among positive integers, there are infinitely many prime numbers. This method of finding a prime number is called sieve of Eratosthenes. Now, consider the integer 42. From this table, it's clear 42 is a composite number because any number which is not prime are called composite numbers. Now try to express 42 in different forms. It can be written as 2 into 21, or it can be written as 3 into 14, or it can also be written as 6 into 7, and their combinations in the reverse form. Now we know there are we see here there are three different representations of 42. Now let's try to express 42 as a product of primes. In each case, it will be 2 into 21 is nothing but 3 into 7. Now 3 into 14 is nothing but 2 into 7. 6 is nothing but 2 into 3. If we look at these three cases where 42 is expressed as product of prime factors, we see the only prime numbers that are involved in each case of representing 42 are 2, 3 and 7. So we find that any composite number can be expressed as a product of primes in a unique way whereas the order in which they are represented may be different. Here 2 appears first, whereas here 2 appears in the second position. So order of these primes may vary, but the prime factors are going to be unique. This is called as fundamental theorem of arithmetic. The statement, let's take down the statement, fundamental theorem of arithmetic. The statement reads this way: every composite number, that is the number which are not prime, are called composite number, and every such composite number can be expressed as a product of primes and this representation, that is the way of factorizing this, and this factorization is unique apart from the order in which the prime factors occur. So this is clearly we have explained using this illustration with number 42. The first we have expressed this 42 as a product of composite numbers, but the way representation was not unique, and then we factored them with the as prime factors, in which case they were unique. We always had only the prime factors 2, 3, prime numbers 2, 3 and 7, but only the order in which they appeared are different. And this is what officially stated in fundamental theorem of arithmetic. The application of this we'll discuss in the next lecture.